and just want to say hi to the, oh, I lost count. We're now at the 7th part of the Atom Probe School, and this part is now about concentration profiles and n-dimensional concentration analysis, or generally n-dimensional analysis. And I think one of the first analysis we might want to do is just a field desorption map, something like that. And I think for a field desorption map, aluminium is probably not a bad idea. Anyway, so let's get right into it. And I will just load the POS file is. The POS file is loaded. Let's just get rid of the GPU. And I'll just, oh no, that's not what I wanted. I wanted to load the color scheme and load the isotope table and add the things. Well, we're going to be working on and per atom basis right now, I think, so I'll just leave it at that. And allocate the ranges in a decomposed manner. And I probably need a mass spectrum for that. Aluminium mass spect range. And by the way, because we had questions, this is not beer, this is tea. It just happens to be in a beer stein. Okay, so let's get the spectrum. Can I do it this way? No. Okay. I just like the command line, sorry. Okay, and let me just move that. Oh no, I think this way. The vertical, we can just make a little bit more space this way, I think. Yep. Good. So we've got all of the. We've got everything allocated, so we can see now where the atoms are, which atoms, which ions, and so on and so forth. And so I showed you before that we can create essentially analysis for any kind of dimensions. And before we just used a 1D concentration profile, but we can use the very same code to do a field desorption map, for example, or a detector stack hit density map, or whatever the hell we want. And I'll just start now with an example of creating a field desorption map. So in order to do that, what we want is we first want to have bin centers in bin edges. And in this case, what we want is we want to do that for pos.detectorx and pos.detector_y. And our bins are going to be, I don't know, this is a 40 millimeter detector, so I don't know, 0.1 millimeter would be 400. Let's say 0.2 millimeters. 0.2 millimeters, 0.2 millimeters. So usually anything much below 50 microns doesn't make sense anyway, because that's sort of in the detector resolution range. And now I can see we have our bin centers variable again here, and it goes from -18 up to +17, so roughly our 40 millimeter detector that our atom probe has. And you can obviously have two of them, one in X and one in Y direction. And now we can say, okay, our voxels or pixels in this case, so I should probably call it pixel, is pos nd bin of our pos, and our distance variables are pos.x and pos.y, and we give it the bin edges in order to create that bin. Did I do something? Okay, let me just have a look into the code. What did I do wrong? Oh yeah, sorry. I was getting ahead of myself. In this case, it's just a histogram. You can see sometimes I mistype as well. And with that binning, you can very easily create a histogram. Sorry, that was my fault now. And now if I look at the if I want to look at that, I can just go and create a new figure and go image scale FDM. And there we go. We've got a beautiful field desorption map of our aluminium dataset. So does every one of you know what a field desorption map is? So one thing you can see here, by the way, so a field desorption map is essentially a density map of hits on the atom probe detector. And unfortunately, when everything crashed before, I just lost my... Ah yeah, no, I didn't lose my sketch from before, that's great. So let me just make sure that our field desorption map is equal in X and Y. And then I go all print screen and okay. So you should be able to see my Krita screen now. So essentially what this thing here is that if you have an atom probe experiment, so this is your sample and this is the detector, then obviously you have, you know, some kind of ion that flies from your sample to the detector. But because your sample is actually not atomically round, so if you zoom into here very, very closely, what you will see is that, well, our tip is made from individual atoms. Yeah. And we are removing those individual atoms. And so what you can see here is that the electric field isn't quite the same for all of the atoms, right? Because here you've got a kind of a facet, and here you've got a kind of a facet, and here you've got a step, and then a facet, and so on and so forth. And most importantly, at these facets here, so this is a low index crystallographic direction. Yeah? This is a low index crystallographic direction. And what happens in those low index crystallographic directions, we get some field distortions and we get some effects that an atom, for example, before it evaporates, it can move a little bit, it can roll up. And so if we look at that locally, you know, we might say, okay, in this direction here, this is a low index crystallographic direction. Then this here is a low index crystallographic direction, and this here is a low index crystallographic direction. And those directions, yeah, will then look a little bit different on a detector. And this is what we see here. And I hope I'm getting it right. I think this would be a... And if there is any pros that do that all day long, they can tell me what crystallographic directions those are, but I believe this would be a 2-2-2 direction, and I'm not going to comment on the other ones. And so for us in atom probe, it's very often very important which crystallographic direction we look at. For example, I expect here to have very good data, and on a new. I expect there to be very good data, for example, in this area here, yeah? Or this area here. And we will mostly see crystallographic planes in this area, around these areas here. Yeah? In aluminium, we will see a lot more crystallographic planes, but this is what a field desorption map is. This is why we very often want to produce those in order to make some to be able to say something about our sample. Also, you know, it might be, this is obviously one crystal because there's no interruption to any of those zone lines or any of those poles, but we might have a, you know, we might have a grain boundary going through here. Then we would be able to see some pole structure here and some other pole structure here, because the crystals would be tilted with respect to each other. And this is something we can see in a field desorption map very easily. And this is why it's interesting to plot those. Also, in this case, it's interesting for another reason, because this is made on a machine with a reflectron. And you can see, for example, that these lines, they should be relatively straight. But because it's a reflectron, it's not entirely straight, but Kamika uses software to sort of to take those distortions out. If I say something stupid in this case, Dave Reinhardt, you can stop me at any point. Yeah. And this is essentially the basis. These detector hits and the distortions are essentially the basis of the atom probe reconstruction. And you can use it to figure out which crystallographic orientation your sample has, or if there's two grains, possibly what the tilt is between the grains, and so on and so forth. And this is something we can very simply do with our binning system to just produce a field desorption map like this. Of course, right now we don't have a scale here. This is just in pixels because now we have God knows how many pixels. But you can do things like looking at what the local density is. You can put a data tip in and say, okay, here we've got 1630 hits, and here we've got 210 hits, so we've got some significant difference in the hit density between the pole and outside the pole, and this is the kind of thing that you can very easily investigate with that kind of binning. Good, now we might want to create a 2D concentration map, for example. And in order to create a 2D concentration map, do we have a workflow for that? Concentration map, great. So we can again create the bin centers and the bin edges. And in this case, we will just use the X and the detector X and the detector Y. And maybe for every 1 nanometer or something. And we want it distance based. Okay, and now again we've got our bin vectors. And in this case, we want to have some. Okay, this is not. We want to divide the data set up into individual POS files. So our pixels would be POS.a. That's the error I made before. I didn't go with the detector X and detector Y, but in this case, it should already work for what we're trying to do. So sorry, I'll show you the FDM also with the ND voxelization system. And now it divides the entire data set up into small sub-data sets, just like we had with the 1D concentration profile. And now we get a variable that's a cell variable with, okay, apparently it takes a little while to load that, so where you can already see, okay, somewhere in the middle we've got more stuff, and on the side we've got less stuff. Did it go X and Y? Let me just check the POS bin centers. And now we've got a variable where we have all of those as individual entries. And now what we can do is we can create a variable concentration, which is where we're using an internal MATLAB function called self_fun. So this is a function that applies another function to the parts of a cell. So it will go through each cell and evaluate that function. And now I remember that since I switched off MATLAB, our concentration kernel needs to be redefined. So it doesn't exist right now, so we'll just redo that. And now our concentration equals, our concentration is self_fun, and the function we apply is our concentration kernel. Our concentration kernel, and we want to apply that to our pixelated variable. And we need to tell it that the output is not going to be an array, but a cell thing. So uniform output is going to be false. And now what it does is it goes through all of those 114 by 120 by 112 cells and calculates the concentration for each one of those cells. And this is what I meant by we need better concentration kernels, because now, do you apply any delocalization in your binning? No, because you can't delocalize individual atoms. So there's no delocalization in there. So delocalization really only works if you, so maybe while it's calculating, I just explain to you what ND means. And let me just create a new slide for that. So what ND means by that is essentially just imagine you have, let me just draw it as, you know, a circle. And what we're essentially doing is, oh, it's finished, so it didn't take all that long to calculate. So if we are trying to put that into some kind of grid, so if we're trying to put that into some kind of grid, what we're doing is essentially saying, okay, does this thing here belong to this voxel, to this bin, or does it belong to this bin or this bin or this bin or any other bin? And right now what we're saying is if it's within, and I'll do the if it's for this bin, then we're saying this thing here is in this bin, yeah, and it's only in this bin. And what Andy is talking about in delocalization, you will find that function implemented for example in IVAS as well, is that, well, you know, this bin essentially has a coordinate system around here, and this is this might be the coordinate origin. So this is our origin. So this thing here does actually belong to a certain extent to this bin and to this bin, yeah? Because it's not like right here, and this is pretty close to the center. But you know, if you have a dot that's, you know, smack bang here, right close to the edge, then you know you could say it's, you know, this thing here. If this is our, you know, bin number 1, 2, 3, 4, so this is number. If this is our origin here, so this would be number 4, 3, and number 4, 4. And this thing here would then legitimately probably be half here and half here. And this is something that we actually haven't accounted for in this case. Because yes, if you have, especially if you have relatively low statistics, it makes the results dependent on the location of the grid. And because of course, if I do it like this, if I move my grid just a tiny bit into this direction, then this atom jumps from here to here, right? So if you have data with very thin statistics, this is actually a consideration. If you don't have very good statistics, if you have reasonably good statistics, then this is not as much of a concern, because you can imagine that, you know, if you have I don't know, if you have a lot of dots here, if you just move that line by a tiny bit, this one might jump from this voxel to here, but another one will jump the other way around according to whatever density you have here. And this is definitely something to keep in mind, especially if you have data with relatively low statistics. The problem with that, of course, is we would actually, yeah, now that I think of it, we could actually implement a weighing function that once we do the voxelization, that for each POS file we assign the atom to all neighboring cells and give it a certain fraction with which it belongs to the certain voxel. So that's actually pretty doable. So if the dot is on the edge of the bins, then you make a decision on whether you want to have all of the ones. Essentially, you want to have a less equal or a larger equal sign to put it into the bins, but they won't get lost. No. They won't get lost. But this is something we haven't accounted for in this version. But now that Andy is actually pushing me. I guess that's also something that should go onto our list. Can one of my co-conspirators in the programming just note that down so that I don't forget about it? But yes, that's definitely something that can be implemented and probably should be implemented. And there are actually pretty good schemes to do that in 3D. So far, what people have done is using a delocalization function, which is a Andy just said Gaussian blur. But this makes the transfer function user dependent, so I think that's even worse. But I can show you a little scheme how this can be done. How this can be done in 3D without any free parameters. So essentially, I draw it in 2D, and I hope it's reasonably understandable in the translation in 3D. So if this is our voxel and our atom sits here, right? Our atom sits here. What I can do is I can partition the voxel and use these respective areas, the reciprocal areas, to define by which percentage this thing will belong to each of the corners. So this will be corner 1, corner 2, corner 3, and corner 4. And I shouldn't call them corners, I should call them vertices, because that's what they are. So let's change that to V for vertices. So this would be V1, this would be V2, this would be V3, and this would be V4. And so the amount that it belongs to V1 is proportional to this area 1 here, and this would be V4, V2, and V3. Now, it's not super easy to read, but I guess you get the idea, right? So it's always the opposite side, and you can do the same things. And let me just do a drawing. You can obviously do the same thing in 3D. So let's put our little thing somewhere here in 3D. And now, in 3D it just works with cubes. I'm not gonna, I think it's a bad idea. I think I'm just gonna confuse you more if I draw it in 3D. It's a little bit hard to draw. But it's exactly the same thing. So you just go for the volume that's essentially opposite your opposite the vertex that's the respective corner, because obviously the origins make up a grid, but also the corners make up a grid. So this grid, the origin, in this case this would be the origins. So this would be, so one of those would be one of those. So it's a shifted grid. So yes, this can be implemented, and this probably should be implemented. So we'll note it down, Andy, and I'm not quite sure if it's going to make it into version 1.0, but it certainly can make it into one of the higher versions. And then you can just create a mass spectrum with quarter atoms or fractional atoms or whatever, and then work based off of that. So yeah, we're always open for interesting suggestions. But I think the transfer function thing is absolutely not helpful. It's computationally much cheaper, because you just need to say, okay, I put some kind of function here and blur everything. But it's not a clean solution, because you wanted to make things independent of the grid, but then you create a dependency on a user input. So that's even worse. Anyway, so what we have now is a cell array of concentrations. And so now if we open this and it eventually loads, you will see that we have now a very large table of tables. And if I click into one of those tables, what I will be able to see is a concentration calculation, just like we had before. This is why it's a 3 times 15 table. And if I look into it, I will be able to see, okay, I can have counts of magnesium, aluminium, silicon, blah, whatever. Yeah. And so, for example, what we could do is we could display the count or the concentration of, I don't know, let's do copper, why not? Relatively easily, and we can do that again using self-fun. Yeah. So I think I have a function for that. Probably not in 2D. Anyway, so what we can do is can call that copper concentration, and that's then self-fun. And in this case, we are creating an anonymous function in there. Bear with me, it's not as complicated as it sounds right now, but we are going to say add x, and what we want is x, and x is essentially each cell. Each cell is one of those x's, and it's going to be x dot what do we want to do? So x dot, so sorry, I need to probably read that from one of the concentration variables. So essentially what we want to do is we want to pull the copper concentration value out of each one of those tables. And if I go right, it should be possible by just doing that by going x dot copper and x dot x dot copper, and x dot format is concentration. X dot format equals concentration. Oh, it needs to know which variable. Sorry. A variable is concentration. And now it just pulls the copper concentration out of each one of those things. And I will just give you the code for that. That's a question up there. Yes, sorry, Andy. So it took me a second to recall that as well. But essentially now we've pulled out all the copper concentration. I can do the same thing. So it's already there, which means we don't need to calculate anything. I could do the same thing for silicon. Obviously, I should probably then rename the variable to silicon concentration. And with that, we've got a 2D copper or silicon map. And I can easily display that as well by going image scale. Now what do you... Im scale. Okay, we can just go into the plots and look up which plots are appropriate for our copper concentration. And you will see there is one image SC, okay? Sorry, my fault. So we'll create a new figure so that we don't plot it into... Oh yeah, image scale. And the image scale actually gives us the ability to also put in the actual distance vectors, right? So we have x data, y data, c data, and that's exactly what xyc. That's what we need. So figure, image scale, and so x, y, and c. So our x is our bin centers 1. Y is our bin centers 2. And our color data is our copper concentration. And now you can see we have some bins on the edge somewhere that have crazy high copper concentrations. So we might want to, change the edit color map. So we might want to have it go up maybe to 0.1. 0.05. So this is in absolute values. This is not in percent. And what you can see is that it's sort of kind of everywhere. Yeah, maybe. Maybe we'll let it go to 2%. And if I go axis equal, just to make sure that they are equal, then I can go and print screen that and compare it to our other figure that we had, and what you can see right here is obviously that there's a lot more copper where this 0, 0, where this 2, 2, 2 pole. I think it's a 2, 2, 2. If you do a lot of aluminium and you know that better than me, then tell me, okay, no, this is a 1, a 1, 1, 0 pole or whatever pole it is. But what you can see right now is that we'll find more copper here, right? So this is something that's pretty interesting that we can see from such a 2D concentration map. Or if you want to have it directly compared, we can also go and calculate our pin centers based on detector X and detector Y, and I'll give you the code in a second, okay? So bear with me for a second. So we'll just calculate the pin vectors from distance, and then we calculate our pixels now based on detector X and detector Y. This will take a second or two. Oh, sorry, still on the wrong. It's on the wrong screen now. Okay, done. And now our concentrations based on detector coordinates and not on reconstruction coordinates, right? And same thing again. So now our copper concentration can be pulled out from here. Our silicon concentration can be pulled out from here. And we can do the whole thing based on detector coordinates. And this is really the power of doing this. Oh, obviously the bins in this case. Sorry, let me just change the bin size. Now we made it 1 millimeter on a 40 millimeter detector. That's not particularly effective. Now a little trick. If you do things more often, if you do the same thing more often, one thing you can do is you can create a favorite. You can set that as a favorite command, so that you can just go and essentially autocomplete the whole block. I will not be doing that right now, but I'll move the whole block up here and make it 0.2 and 0.2, just like we had before. And then I can rerun the... Did I do something wrong? Oh. Of course I did something wrong. What else? I deleted one of the brackets. And now we rerun the whole thing. And this is really the power of having everything scriptable, okay? Oh. And I accidentally sent everything just to Valentin, who already knows a lot of this. Right, and so now it's still running, but it will take only, however long it took just before, a couple of seconds, and we will have a new copper concentration map popping up on our screen, or me on my screen. Didn't take that long before. Obviously, we wouldn't have needed to calculate the silicon concentration as well. That's redundant. We haven't been using that. And if you look into our code, there is actually a whole lot of different distance functions that you have. So right now, I've shown you obvious distance functions like detector x coordinates, detector y coordinates, x, y, z coordinates, and so on and so forth. But you can also go and calculate things like distance to a point, distance to a line, distance from a mesh, and this is essentially what a proxygram is. Distance to a plane, we give you all those different distance functions, and you can use those distance functions and then go and plug them into the bin vector from distance function and the pos-nd bin function. And then you can come up with all kinds. Why does it take so long? It was much faster before, just right now. Oh yeah, there we go. And now we have our equivalent detector copper map. And let me just go and make the axis equal and edit the color map. Maybe, I think, what did we have before? 2%, something like that. Yeah, it looks all right. I mean, you can still see the precipitates with the copper and the copper deposited, but you can see the copper in the at the two poles that we saw here. And let me just go old print screen and move down to the tablet. And you can see if you compare the two, if you compare the two, oops, that's not what I wanted. If you compare the two maps, you can see, okay, this pole here has more copper, this pole here has more copper. I mean, if you do a direct overlay, you can obviously see those two. But yeah, I guess you all get the idea of why of what kind of analysis you could do this way, and it gives you the full freedom. So the last thing I want to show you in this session now is actually how to do a voxelization. So we had 1D concentration profile, we had 2D concentration profile. Obviously, you can do a 2D concentration profile for a region of interest. You've learned in the last session how to create a region of interest, how to do a transform into the region of interest. So you can very easily make yourself a little script that takes whatever you have in a region of interest and creates a 2D concentration profile from that. So this is something that's very easy to do and then very reusable. And now we want to go 3D. So in 3D, obviously you can do the same thing that I did just now. And you can go and just change everything to a 3D version of it. So have our bin centers and bin edges, not with detector space, but with regular reconstruction space. You can also do it with detector space, of course, and you have pos detector x, detector y, and the ion index. Yeah, this would be your z coordinate. You can do that as well. But for now, we just do it with .x.y.z, and I'll do it with. This is large enough to probably do it 3 nanometer binning. And now I will actually do the pixel function as a voxel function. Call that voxel, and a voxel is just a volume pixel. That's where it comes from. And the pixel is a picture element. And what you will see is that this is not really the fastest way to do it. So if you want to do something like have an advanced concentration kernel, go through your individual sub-POS files and really, deconvolve things. Maybe you have a problem where you need a voxelization and an isosurface or some information about something where you have some bad overlaps between two elements. Silicon and nitrogen, for example, right? If you would go and take silicon 29 and silicon 30 as the basis for calculating the silicon content and subtracting them from the rest in the peak at 14 for the nitrogen, then and the concentration works exactly the same as before, but now you can see we have our voxel is 39 by 38 by 54 cells, so it's quite a number of cells. What do you mean? What I did for pics? Thank you. And maybe we're going to time this one as well. You will see that 39 times 38 times 54 is a lot. I don't know, some 10,000 cells or something like that. So it's quite a few cells that it will need to go through and apply our concentration program to. And if anyone from the MathWorks is listening, I really want the parallelized version of that. So this would be something where it would be really great if each one of those concentration kernels could just simply run on one single core of my PC here, because I believe this PC either has 16 or 32 cores. Anyway, a lot of cores, so this makes it a lot faster. Which also brings us to one of the upsides of having scriptable things. So most high-performance computing centers at universities have licenses for MATLAB high-performance computing servers. So all of those scripts you can just send over to your high-performance computing center and have them running on however many cores they're willing to give you, And if it's a high-performance computing center, very often you can get 100 cores, you can get 200 cores. And you can, for example, try and do a calculation on your POS file with 50 different settings, 100 different settings, and just have all of those CPUs crunch each one of those parameter sweeps individually. But if I can have a wish from a MathWorks, it would be that those cell fun functions and array fun functions really would be parallelized. That would be very, very helpful. Anyway, so what I showed you right now is actually the slow version, and I will show you for the voxelization a faster version. The slow version has the upside that still, once you've calculated the concentration, it's all there. Yeah. So all of the atoms, all of the concentration calculations are there and all of the information is there. So you will see which concentration you have, how many unranged you have, so you can voxelize the unranged ones. And once that's calculated, it's all there. So very often what I do in this case is just I start the concentration calculation and then go and make myself a tea. Or do something like that. And then it will run for a couple of minutes and then I will have all of the concentration information here in this one variable and don't need to recalculate it all the time. But if I just want to quickly know, for example, if I want to quickly calculate an isosurface or something like that, and I don't care if it's super accurate at the time, then one thing that is very easy that we can do is to just voxelize the individual atomic sub-pos files. Yeah, so to just get a count per voxel for each of the species. So I'll just go and say, okay, give me all the counts for copper and give me all the counts for all of the atoms. And this is something that can be calculated much, much faster than applying a concentration function to each of the individual cells. Okay, which means while this is calculating, obviously with the voxelization we are going towards calculating isosurfaces. So who of you has never heard about an isosurface? Anyone? Raise your hand. Everyone's heard about an isosurface. Okay. So, thank you, Martina. An isosurface is essentially equivalent to is essentially equivalent to the height lines in a map. And this is not a particularly nice display of that. Do we have something? Some nicer. Okay, let me just draw that for you. So let me just create a new. So just imagine you're a hiker, right? And this is our altitude. And this is our distance variable. And you are going hiking. And if you're not in Germany, then it's not going to be flat. So if you're in Austria, if you're in my old hometown, then this is not going to be flat. But you are going to be hiking somewhere here. And you are probably going to have a hiking map. And what that hiking map shows you is essentially locally what altitude you have. So this might be 1,000 meters, this might be 2,000 meters, this might be 3,000 meters. And in Austria there's nothing with 4,000 meters, so 4,000 meters is up here. Obviously, if you look from the top, the whole thing is going to look more like this. This is maybe what your mountain looks like if you look from this is like the outline that you have from the top. And so this was our 1,000 meters line, our 2000 meters line, our 3000 meters line. And what you can see is that it's not possible for you just by the lines to see where the top is, because we have no line at 3,495 meters. That's what the top here is. And this is essentially what an ISO line is. Yeah? So this is an ISO line. And we do the same thing in 3 dimensions, okay? So we create an isosurface. And now the calculation is actually finished, and you can see it took 369 seconds, so that's about 6 minutes. No, that's about 4 minutes. Now we can do the same thing as before. So we can, for example, in this case, probably we want to do silicon, because I think this had the nicest precipitate shapes. So silicon concentration. And now all I need to do is just pull out the silicon concentration from that variable. And you can see here that I have a variable now with 39 by 38 by 54 entries. And I can actually go and... this version of MATLAB does not have the volume viewer. I am very concerned. Anyway, we'll do it without the volume viewer, because that means that some of you won't have it either. And so what we can do with that silicon 3D, so this is now a 3D map of where the silicon is. And one thing we can very easily do is just take a slice out of it and essentially use it as a 2D concentration profile. So we can go and create a new figure, and bin centers 1, bin centers 2. Yeah, we can keep that, and we use the silicon concentration. And I only use bin centers 1 and 2 because these are, I know these are the X and Y's, right? And we want to do an X and Y map, so we can keep that. And we want the silicon concentration, and we want all of the X entries, all of the Y entries, and maybe one in the middle, maybe number 25 in Z. This would still give us a 3D thing, but we want a 2D thing, so we can use the squeeze command. So squeeze just means, I'll show you in a second what squeeze means. And here, ta-da, I get a 2D concentration map of my silicon. So the shading here is, by the way, the shading is flat, and we can also go and shading and use interpolated shading. Then, oops. Why is it a little bit slow now? Anyway, so you can do interpolated shading and it smooths the whole thing out. View. Okay, I forgot how to do that. But essentially, if I go test equals silicon concentration all 25, then you will see that where's our test? Oh, why has it gotten so laggy? Something is not quite right. Oh no, it did the squeeze by itself. Huh. Anyway, so Usually what we want to do first, if we calculate an isosurface, and let me go back to the tablet drawing. Oh, you weren't able to see some of my beautiful drawing here, is to see if we, might have multiple hills. And if we have multiple hills, we want to know where the valleys are, how deep the valleys are. And in order to do that well, the first thing I usually do is to look what the statistical distribution of my what the distribution of voxel values is, right? So the way I can do that is using so-called linear indexing. So what I want to do is create a histogram, create a new figure, and in this new figure, I want to create a histogram of, I want to create a histogram of my silicon concentration. And now what you can see is that I used only the colon and not the 3 entries. And this means MATLAB, please take the whole 3D array as a 1D array. Yeah? Because otherwise it will try to do a histogram in all 3 dimensions, which is nonsensical in this case. And I want to have that. I've got a lot of bin values, so I can probably do that with, I don't know, 200 bins or something like that. I can explicitly go and also define the bin edges, but I'm too lazy for that now. We will see what the bin edges are anyway. And now what you can see is that there's obviously a lot of values with 0. And then some values in between. And we will go and zoom in. So that we can see, okay. It goes down here and then maybe a little bit up here. But I guess a good guesstimate would be somewhere we'll just give it a try. So if you do that kind of histogram, here obviously the separation is not as great because we don't have a large volume fraction. But very often what you will see, for example, if we took the superalloys data set where you have got very good partitioning, what you would see is that if we go frequency versus concentration, that there's obviously a lot of zeros, and then there might be one hump, and then there might be another hump. Yeah, something like this, where essentially this would be any sort of voxels at the corner, and this might be your gamma, and this might be your gamma prime, and then this would be a good value for our ISO value, or for our value to partition between our valleys and our troughs. But let's just give it a try. And now I will actually open the workflow. Sorry, and I'll copy all of that other stuff for you as well. Open our work isosurface, because there's one trickery in this, and this is there's some inconsistency with MATLAB's voxelization, which is a little bit annoying. So you can see that essentially the grid vectors, or the bin center vectors are swapped between the isosurface algorithm and the global coordinate system. That's been in MATLAB forever. It's just something that you need to know. And so isosurface is actually a built-in MATLAB command. And so I call my isosurface FV, and maybe in a second it will be a little bit more clear to you why it's called FV. And FV is an isosurface. And for the isosurface, we need the X, Y, and the Z grid, and the values and the iso value. And our X, Y, and Z grids are the bin centers. So in this case, bin centers 2, bin centers 1, and bin centers 3. So that inconsistency is not my fault, that is absolutely 100% MATLAB's fault. Okay, you just need to remember in the isosurface, the X and the Y coordinates are flipped. God knows why. And then we want to have our silicon concentration as the value. And I think as an ISO value, I had 10% or 0.1. Oh, okay, so image scale has the values flipped as well. I didn't know about the image scale. And now you can see we have an isosurface. And that isosurface is right here. And it consists out of vertices and faces. And you'll hear a lot about vertices and faces tomorrow. So essentially, if we want to display a 3D mesh, so any kind of free-form geometry in 3D, the way we do that is by defining certain points. Let me make them certain points. And then having sort of object, oh, this is wrong. And then having in 2D lines between them, and in 3D, if this was 3D, then it would have triangles. And so the vertices, these are the vertices, and these are the faces. In 3D, of course, we've got vertices, faces, and lines. But these are geometric primitives that we work with. And we can actually display them in 3D easily. So we can go, I'll just create a new figure, a new axis. Figure, axis, so that we have somewhere to plot. And then I can go patch FV. And patch is the display command for these kinds of things in MATLAB. And you can see that maybe 0.1 was not really a great ISO value. So maybe I chose 0.0. Maybe let's do a 2% isosurface. Something is bugging MATLAB down right now here. I don't know what it is. Usually this should go much, much faster. And one thing I'm going to do is just define the face color straight away so that we don't get a black patch. And let me just make it green. And also give the face some transparency. And so we'll make it 50% translucent, right? And there we go. We have the magic. So now we have a very nice isosurface. Maybe we'll make the axis equal as well. Axis equal. And now you see we've got very nice isosurfaces from our precipitates here. Okay, and with that, actually, I will conclude this part of the tutorial. No, one thing we can do is APT EFI, or maybe it's called axis APT phi now. What is our APT phi axis called now? Can any one of my people give me a hint? So we have a convenience function that if you have any kind of 3D plot and you have it upside down and maybe the coloring is not there and everything, we just have a very quick function that can fix that for you. Because at some point we all have decided that atom probe datasets need to be in a way that the big part is at the bottom, because otherwise the atom probe dataset will fall over and all the electrons will fall out. So axis spatial APT phi, thank you. And now we have that in a very nice atom probe display. Okay, and what we will do tomorrow is actually we will take off at this point and continue the analysis from there. And because today, the rest of today, we will actually have Konstantinos Hatzoglu, who used to be at Rouen for a very long time, but is now in Norway, who has done a similar thing than we did, and it is program a lot of analysis in MATLAB, but with an exactly opposite approach compared to us. So what Konstantinos has done is he's programmed a graphical user interface for his analysis. So Hisham is asking if it's possible to filter isosurfaces on size. And this is absolutely possible, and tomorrow we will do a ton of that. We will look at how to split them up, how to filter them by size, how to treat them, how to do funky things with them. So there's a ton of those things that we can do, and we will actually get to that tomorrow. Okay, but with that isosurface, I will leave you for today and leave you in Konstantinos' hands. And as always, I will post the rest of the code. And I will post the rest of the code. And I think that one I had already. We'll post the rest of the code, and will I save the workspace? Yes, I can save the workspace. I will save the workspace so that we can send it out for tomorrow. But you know what? I think we will recalculate it tomorrow, because I think we will use the superalloy tomorrow because it's got some nicer looking things in it for isosurface analysis. Or maybe we'll do the aluminium. Who knows? But yeah, I will save the MATLAB workspace as well so that we can potentially do something with that. And with that, I'll give you a 15 minutes break. I'll switch off the recording now, and I'll see you at 1:15 for the session with Konstantinos.